Over the last few videos, we learned graphs, what they are, how to store them, and how to explore them with BFS and DFS. Today, we finally put them to use. We solve a real problem, the kind that shows up in interviews. It is called number of islands, a problem that scares a lot of people, about to feel easy. Let me first paint the picture. Imagine you're looking down at a map from the sky, like a satellite view. The map is a grid. Each cell is either land or water. Let us say land is a 1 and water is a 0. An island is simply land cells that touch above, below, left or right. Touching land is one island. And your job, the whole problem, is just this. Count how many separate islands are there on the map. That is it. Look at the grid and tell me how many islands. Simple to understand, right? So let's count this very grid together. Top left, there are 2 land cells touching each other. Somewhere on the right, there is one lonely land cell sitting all by itself, surrounded by water. And at the bottom, another small patch of land joined together. 3 islands. Your eyes saw that in a second. Easy for a human, but a computer cannot just look. So how do we actually solve this? The trick is to see this grid as a graph. Think about it. Each land cell is like a node. And if 2 land cells are touching, that is like an edge between them. So an island is nothing but a connected group of nodes, a connected component. And we already know how to explore a connected group of nodes, with BFS or DFS. That is the whole idea. Once you see the grid as a graph, this is a problem you already know how to solve. So here is the whole trick, in one line. The answer is simply how many times we have to start exploring. Here is how. We walk the grid one cell at a time, like reading a page, left to right, top to bottom. For each cell, we ask one question. Is this fresh land we have not visited yet? If it is water or already visited, we just move on. But the moment we step onto a fresh piece of land, we have found a brand new island. So we add 1 to our count. And then, this is the key. We launch a traversal, BFS or DFS, that floods across every land cell connected to it and marks them all visited. That flood is what stops us double counting. When our walk later reaches those cells, they are already visited, so we skip them. So every fresh start is one island. Count the starts and you have your answer. Beautiful, isn't it? Let me walk through it carefully so you can see exactly what the traversal does. We start scanning, cell by cell. The very first cell is water, so we skip it. Now we hit our first land cell. Unvisited. Island count becomes 1. Let us launch the traversal and watch every step. We stand on this cell and check its 4 neighbors. Down, it's water, so we skip it. Up, the edge of the grid. Left, it's water again, so we skip it. Right, land and unvisited, so we go there. We move to that cell and check again. Down is water. Up is the edge. Right is water. Left is where we came from, already visited. Nowhere new to go, so the traversal ends. Island 1 is fully marked. We keep scanning. The next land cell we reach is already visited, so we skip it. No double counting. We scan on and reach the lonely cell on the right. Unvisited. Island count becomes 2. We check around it. Down, water. Up, water. Right, the edge. Left, water. No land anywhere, so this traversal stops right away. We keep scanning and reach the bottom patch. Unvisited. Island count becomes 3. Let us follow this last traversal step by step. We check this cell's neighbors. Down, water. Up, water. Left, water. Right, land, go there. On this cell, we check again. Down, land, unvisited, go deeper. On this cell, every direction is water, the edge, or already visited. A dead end, so we go back to the previous cell. Back there, its other neighbors are water or visited too. So we go back again, all the way to the start. Nothing left to explore. The whole island is marked. 3 traversals, 3 islands, exactly what our eyes told us. Now let us turn the idea into code and run it on the grid line by line. We will use DFS in Java. Watch the call stack on the side. It is the recursion made visible. These 2 loops scan row by row, column by column. The first cell is a 0, water, so the if line is false and we move on. The cursor reaches the next cell, a 1, fresh land. The if line fires. Count goes up to 1 and we call DFS here. Our first call is pushed onto the stack. Inside that call, the first line is the safety check of the grid or water. We are on land, so it passes. This line syncs the cell, sets it to 0, marking it visited. Watch the digit flip to 0 on the grid. Now the 4 recursive calls in order. Down is water, so that call returns at once. Up is off the grid. It returns too. Each is a quick push and pop. The third call is right, and right is land. So DFS goes into that cell. A new call is pushed on the stack, and control descends 1 level deeper. Down here it syncs this cell too. Then tries its own 4 neighbors, but they are all water, the edge, or the cell we came from, already visited. Nothing new. So this deeper call returns. It pops off the stack, and only now does control come back up to the first cell to run its last line, left. Left is water, so it returns. The first call has now tried all 4 directions, so it pops too. The stack is empty. Island 1 is fully flooded. Back in the loops, the scan continues. The cells we sank are zeros now, so the if line stays false. We skip them. No double counting. The cursor reaches the lone cell on the right, fresh land. Count becomes 2. DFS syncs it. Every neighbor is blocked, so the single call returns at once. The scan reaches the bottom patch, fresh land. Count becomes 3, and DFS is called on this cell. The first island 3 call is pushed onto the stack. It syncs this cell, then tries its neighbors. Down and up are water, but right is land, so a new call is pushed, and control descends into that cell. Down here it syncs the cell and checks again. Down is land once more, so it pushes yet another call and dives 1 level deeper. The stack is now 3 tall. This deepest cell sinks, and every direction around it is water, the edge, or already visited. A dead end, so this call returns and pops off the stack. Control is back 1 level up. Its remaining neighbors are all blocked too, so this call returns and pops as well. And back at the first cell of the patch, its last direction, left, is water. So the final call returns, the stack empties, and island 3 is fully flooded. The scan finishes the grid, and we return count 3. 3 fresh starts, 3 islands. Exactly what our eyes told us. That is the entire solution in Java. Prefer C++? Same loops, same recursive DFS, only the syntax changes. And the same idea once more in plain C. Pick whichever language you are comfortable with. Quick word on speed. We touch each cell only a small fixed number of times. So the cost grows just with the size of the grid. Rows times columns. Very efficient. And one note, we used DFS, But BFS solves it the same way. You would just swap the recursion for a queue. Same plan, same answer. Let us bring it together. The whole solution was 3 moves. Walk the grid, count each fresh piece of land, and flood fill it so we never count it twice. The number of fresh starts equals the number of islands. That is the entire algorithm. And the real lesson: the moment we saw the grid as a graph, this became a problem we already knew how to solve. Once you can model a problem as a graph, you can reuse everything you know about graphs. That is what makes this skill so powerful. Next time, we will take on another classic that uses this exact same idea, a problem called flood fill. So see you there.